Alright, so today's video we're going to talk about different types of electrical drawings. Well, this is going to be a review from first year with a couple extra little tidbits in there for you. So we're going to talk about electrical control drawings and diagram conversion. I'm sure you remember in first year you did a diagram conversion assignment when you're taking a wiring diagram and converting it into a schematic diagram. Right, so we're going to be doing that again. Then also going from a schematic diagram to a wiring diagram. So it goes both ways, right? But really nothing new from what you did in first year. All right. So outcomes of today's class, right? We're going to identify 4 basic electrical control drawings. We're going to identify schematic symbols that you're going to see often in the schematic drawings and wiring diagrams. And we're going to describe the sequence of operation by reading a control schematic. And that's the beauty of a schematic diagram. They're excellent for showing you the sequence of operation. Alright, so the different types of drawings. First one here, we've got a block diagrams. Right? It's a general overview of the system installed. They're very, very simple diagrams. It pretty much shows you the relative location of each component, but not how it gets there and not where it is necessarily in a room. And it's showed using blocks or triangles or squares or circles or pentagons or whatever you feel like that day. All right, so here's an example of a block diagram. We have the main alarm panel here, so this is an alarm system. All right, and we have our transformer feeding 120 volts in, stepping it down to say 12 or 24 volts. All right, we have a key switch over here, alarm switch 1, 2, 3, and 4. We've got your junction boxes with a bell, which is your signaling device. Right? So it's a very, very simple diagram, just kind of showing you the relative layout of the components in that circuit. Okay? There's another one here for a solar panel system. All right, so we got the sun, solar panels. It kind of shows you how things are processed here. All right, solar panel to a DC link. A DC link is going to be connected to an inverter, DC to AC, and that's going to go into your fiber optics and a control board for communications. Another fiber optic cable to a control room. Then we got the inverter feeding into the 3-phase line filter and a transformer. Right, and then through fiber optics is also going to be being controlled from the control room, and then your circuit breakers, right? And then hook it up to the utility AC power, right? So again, very, very simple. Just shows you the relative interconnection of devices. All right. So here's an interconnection diagram. All right. So it's how one component is connected to other components. Most common is a termination schedule. Right, so it's going to have pretty much a legend showing you where things are going to be terminated. Another type is a pin-out diagram, how a conductor is connected to each pin on a multi-pin plug or receptacle. So it's pretty much showing you if you have like a 12-pin receptacle or plug, it's showing you what wires are hooked up to what pins and where it's going to be going into the female or male side of that plug. So here's an interconnection pinout diagram. All right, so this is the female side. This is the bottom view here. All right, so you got your brown, pretty much all the colors of the conductors going to each pin here, right? And then the other side here, we got your socket, and it's a side view, right, showing you all those colors and where they're going to, 1 to 8. And then going to the male plug, it's showing you what connection points they're going to be using. And it goes from 1 to 25 here. Right? So it's pretty much showing you the relative interconnection between the female and the male side of the circuit. Right? And then you have a field cable termination schedule. Pretty much is the same thing as what this is. It's just showing you the interconnection between those two sides so you don't mess it up. All right, here's another one. right? Showing you which, pretty much which pins or terminals are being interconnected together. So line 1 or L1, L2, L3 are your three-phase voltages coming in, the three phases there, right? 1 and 2 are going to an external interlock, right? 3 and 4 are going to a stop device hooked up in parallel with an up and a safety device or a pressure switch. Okay, so yeah, again, they're very simple. It's pretty much just going to show you the interconnection between different points on receptacles. Then we got wiring diagrams. Probably my least favorite diagram. Right? They can be very complicated, as you're going to see here. But it does show you the detailed wiring of an electrical device, equipment, and the system. So it's going to pretty much lay out, it's the most realistic layout of where your equipment's going to be. So see on your bench, when you're hooking up a motor or a contactor or a motor starter, right, you're going to have the relative location. Okay, top left corner is going to be my motor, top right corner is going to be my motor starter, top left corner or right corner, whatever, is going to be your transformer, etc., etc., right? So it's the most realistic layout of where your actual equipment is going to be. Okay, it says shows relative location of the complete install. So here is an example of a wiring diagram. As you can see, it gets pretty complicated pretty quickly, right? Trying to follow these little lines and where they're actually going, right? So we can see here we got a transformer, top left corner. Above that, a little to the right, we got alarm switch 3 and 4. And then bottom left, we got alarm switch 1, and then alarm switch 2. We got bells over here, and yeah, it gets pretty complicated, right? But here we have our main alarm panel, so we can kind of see what's going on with the basic install of where things are going to be coming in and out of the panel. So that's a nice thing, right? Here's a little more complicated. The next slide is quite drastic. Great. So we're always going to draw a wiring diagram as if it's de-energized. Same with a schematic diagram. Yeah, we draw that in the sense of safety, right? We want the circuit to be de-energized state, right? And that mostly applies to relays and contacts. We're going to try to draw them in the de-energized state unless the contacts are normally closed. Then we're going to draw them normally closed, which of course means something in that circuit is going to be most likely energized. All right, so here's another wiring diagram. These are all real. Okay, this is a pump wiring diagram. So trying to walk through this guy, good luck. Trying to convert this to a schematic diagram, good luck. It's pretty darn complicated, but you can do it. All right, but again, it's just going to show you the relative layout and the interconnection between the devices and those wires. All right. There's another one here showing you a holding tank with the pump, right, and the panel. Okay. So one quick note here, it says down here, it says nodes are okay in enclosure. So when we talk about a wiring diagram, not sure if you remember from first year, wiring diagrams, if you have a node, that means that's a break and a splice in that conductor, right? So if you show on a wiring diagram, say we had a node right here, okay? And this is on your bench in the lab. Well, that means that you physically have cut the wires in the lab and spliced them together, which we're not ever going to be doing, right? So we never usually show nodes on a wiring diagram unless, okay, we can see that inside of this panel, inside of this device here, right, this enclosure, they're showing an internal splice, which you wouldn't be doing. It's already built into that system. All right, so usually we never show a wiring diagram with a node, right, because that means that you've cut the conductors in class, and we're not going to be doing that. Right, so again, in the enclosure or in a specific device, you may have, like over here, right, this is inside of an enclosure. You can see it's capped in there. We have splices going on. That's not something you would be doing just outside or on the bench. Okay. All right. Wiring diagram drawing rules. It says devices are shown in geographic position with respect to each other. So again, the layout of on your bench, say where each switch is going to be, where your transformer is going to be, lights, and all that stuff. Okay. It says here, lay out your equipment on your bench to look similar to this. Right. Well, obviously you're not at the bench right now, so you can't really do that. Right. But if you were in the lab right now, you'd be laying out your relay system, your contacts, all your push buttons, your normally open, normally closed push buttons, your 220 volt lights, you got a transformer, and then your source. So you would lay it out just like this. If you were looking at the top down onto this picture here, you would lay it out. Right? Okay, so with that layout, right, they're showing an interconnection between your common terminal here, right, going to your secondary side, or sorry, your high side of your transformer, right? And it's showing a big X saying, don't do this, right? And it's Xing out this node here. And like I said, with the wiring diagram, we don't show nodes because that means you physically cut that wire in class and you're splicing it together, right, to be in parallel here. What you would do instead, you would bring from your source, line 1, you would come to the high side of your transformer, and then you would just stack your another lead on top of that and branch off in parallel instead of cutting those conductors and splicing them together. Okay? So you did this in first year. You didn't cut your conductors and splice them together. You actually stacked the conductors. So we have to come in with 90-degree angles and 45s out. So in with 90, 45s out. All right. Okay. Then schematic diagrams. All right, schematic diagrams are my favorite. They show the sequence of operation for a circuit, and usually when you get a wording like in a booklet saying, "Hey, I want you to hook up so that this happens and this happens and this happens," well, they're telling you a sequence of operation, so you're pretty much just turning those words into a schematic diagram, into a drawing. So it's a quick snapshot of a circuit, and it really shows you what's going to happen to that current as it's flowing throughout that circuit. The physical location is not represented in a schematic diagram at all, right? And it's the absolute best drawing to troubleshoot your circuits. And that was saying that you have to make sure that your schematic diagram is hooked up the same on your circuit as it is at the actual diagram, because if you have a circuit that's hooked up a little bit differently, then you go to your schematic diagram trying to troubleshoot it, you're going to have a harder time because they're not going to match, right? So that's where your wiring diagram going to a schematic diagram conversion, or vice versa, is crucial. So schematic diagrams, also known as an elementary or ladder diagram, is the king of the diagrams, right? We're going to have, this goes back to first year here, with your control devices, all your control devices, so push buttons, thermostats, pressure switches, whatever, a control device, are always going to be located on the left-hand side of a schematic diagram. We always use horizontal and vertical lines, right? So we don't do diagonal lines or wavy lines or whatever. We have nodes in schematic diagrams showing splices, so we're not going to be doing the 90 in and then 45 out of our terminals here. We're going to be doing an actual node showing a splice point to come down, right? And don't forget your nodes, they're going to be actually on hooking up to your transformer or your poles. Okay, and then we always draw, in this case, a circuit de-energized, so the de-energized state here. Now, with the exception of your contacts, this contact here is a normally closed contact, which is going to have light 2 energized right now, and that's okay. You can only do it so much, but if you had like a single pole, single throw switch, say, controlling a light, you would just draw the single pole, single throw switch open with that light de-energized, if you can. Okay, so, going back to the controls on left-hand side, and your loads, whatever they are going to be on the right-hand side of your schematic diagram. All right, we go through, here's one, this is not acceptable. I don't care what you do for practice ones. You can write it on the back of your hand if you want. I don't care. But when you're handing in your drawings or doing them for labs, try to make them nice and tidy using your template, just like you did in first year. All right, so going through schematic diagrams, plans. I'm sure you guys recognize plans from first year, right? An acronym. P is based on polarity, right? So we got to talk about or label the source of our circuit, right? Identify the poles. If it's DC, it's going to be positive, negative. If it's 120 volts, line 1, line 2, or line 1 neutral. 240 or 208 is going to be line 1, line 2. Then X1, X2 for secondary side of your transformer, H1, H2 for primary side of your transformer, etc. Right? So you got to put the polarities in and identify usually what voltage and what type of voltage you're using for that circuit. So in this case here, we have a 120 volt AC circuit using your arrows going to each side saying from this pole here, line 1 to ID, I have 120 volts. Okay. L stands for label everything, right? You have to label the contacts, you have to label your switches, your control devices, your loads, everything, right? Big thing they're talking about here is your contacts should be labeled the same as what that what coil is controlling them. So going back here, it says I have my relay coil right here is CR, right? And I have these contacts here labeled CR, which means this this coil is controlling these contacts here, right? Because you can get into the schematic diagrams, we're going to have multiple coils and multiple contacts. You need to know which contact is being controlled by which coil, right? To know the actual sequence of operation. Alignment. A for alignment. Horizontal and vertical lines only for schematic diagrams, no diagonal, no squiggly lines. All right? You have to align your controls on left and the loads on the right. So you can see here, everything's nice and aligned. You can draw a line straight down here and get these two contacts, right? The spacing here is all the same for your control devices, and everything's nicely stacked here. All your loads are in a perfect line here, nicely stacked. So that goes back to your first year using your template. All right, for alignment. N is for nodes. Node, again, is a splice point, a connection between your wires. Right? So if the lines just cross, which is okay, that means they're not spliced together. They're just laying on top of each other. There's no connection. Right? Your nodes identify a splice point. So I think we have an example of that in here, but you could have just a wire crossing over another wire. If there's no node, that means there's no splice. They're not electrically connected at all. And then S is for symbols. You got to use the proper symbols the proper way. So you're going to be going back to your ILMs, looking for those symbols you need for, say, a float switch or a pressure switch or a thermostat or something, right? And you're going to use your template to then draw out that symbol and make sure you're drawing it the proper way. All right, so you have to go through every time you do a schematic. Now, not necessarily a practice drawing when you're trying to figure out a schematic. We're talking about when you have a schematic figured out, you're trying to do a good copy of it, you're going to use plans and go through the polarity, the labels, alignment, nodes, and symbols. And if you do all of that, then your schematic diagram should be worth full marks. Okay. All right, then we're going to talk about schematic symbols now. So this is module A, right? Pages 10 and 11. That might have changed based on new updates on the modules, but it should be around 10 and 11. Okay, so again, remember this from first year. It's pretty normal stuff, right? This symbol here is going to be, a normally open push button. Okay, it's momentary, so you have to push it down. It's going to make contact here in two places, but if I release my finger from that button, it's going to spring back up, so it's momentary. It doesn't latch in place. So momentary contact device that closes a circuit when pressed. Then we have a normally closed push button. Again, momentary. When I push it down, it's going to break in two places here, but it's only momentary. It'll spring back once I release my finger or that pressure. So momentary contact device that opens a circuit when pressed. Then we have push button interlock here. Right? We didn't really talk about push button interlock in first year. what push button interlock is, it's two momentary contact devices that are mechanically linked. So this dotted line here means that these are mechanically linked together. So if I push down on top here and push this normally open side closed, that means it's mechanically going to push down on this normally closed side and push it open. So mechanical interlock is I can have, say, two motors here, right? So if I push down this guy here, this guy, the normally closed side motor is running right now, and the normally open side motor is not running. So if I push this down, it's going to break here, right, turning off this motor, and when these contacts make up here, it's going to turn on this motor, which means those two motors can't be running at the same time, right? It's mechanical interlocked. Right, and then of course this guy here is the combination of these two, so our normally open, normally closed push button, which is what you usually always ever have, the normally open side and then the normally closed side. You have your plunger here, and then you have your pole, right? You have two makes and two breaks, right, based on normally open and normally closed push buttons. Getting to contacts, right, you have your normally open contacts. They're drawing. You see you have no connection between for your current to flow. Right, closes a circuit when it's the control relay is energized. So the relay coil that is connected to this contact, when that coil is energized, these contacts will close, turning on your circuit. Right, and then we have the normally closed side contacts. If you operate that coil, it energizes. It's going to open these contacts, turning off your circuit. All right, here's a little diagram here. So you have an iron core with a wrap of coil around it, right? And that's going to be your control coil, right? Which is, if you put a current through that coil, it's going to be creating a magnetic field. Magnetic field is causing this armature to pull in, which is going to close these normally open contacts. And if I close these contacts here, right, you can see that I have now a path going through to my load. Right, and if I de-energize this circuit here, this coil, right, this armature is going to spring back. There should be a return spring here, right? Maybe that's what this is here, right? These contacts are then going to open, turning off my circuit. Okay. Then we have normally open pressure or vacuum switches. So that's that symbol there. Okay, it kind of looks like a float switch, but with the ball cut in half, right? These switches are devices that close at a predetermined pressure or vacuum setting. So as you can see here, this one is normally open. You got to think about when you're buying your switch, what gravity is going to be doing. So right now, gravity is pulling down on this pole, which is keeping it open. So we're going to be calling it a normally open pressure switch. Unlike this guy here, gravity is pulling down on the pole here, which is keeping it in contact with this terminal, which means it's a normally closed pressure switch. Okay, so they're going to be showing you different devices or different control devices in different operating states, and you have to determine if it's a normally open or normally closed. Right, so if I pushed this guy open right now, okay, if there was pressure in here or vacuum, I could ask you, hey, is this a normally open or normally closed pressure switch? And it would still be a normally closed pressure switch. It's just a normally closed pressure switch that has been opened. That's all. So you gotta really look at those devices and try to understand what's going on. But we always draw, before I move on, we always draw devices again in a de-energized state or in a state where there's no liquid, there's no pressure, there's no heat. Okay, so in this case, there's no pressure in whatever this is, so the device is just going to be hanging there. Or pretty much you're buying that device off the shelf at Home Depot. Right? It's not actually hooked up into a circuit yet, or put in a tank or a vacuum. Right? It's just sitting there, so you got to look at that state, and that's going to tell you whether it's normally open or normally closed in normal conditions. All right, there's a pressure switch here. Pressure switches are used a lot on cars, if you didn't know that. But you can use them out in the industry too. Just an example of one. So you get your vacuum line hooked up here, right? And it's going to be like a little rubber diaphragm inside there, which is going to be sucked up or pushed from vacuum or pressure, and it's going to close some contacts or open contacts inside. There's another example of one there. Vacuum switches or pressure switches, right? Telling you the pressure or vacuum there. You can see you got your common terminals, right, where your power is going to be coming in. Then you can choose from normally open or normally closed, or both, right? Pretty much just like a relay, but just using pressure or vacuum instead of a coil. All right, this one here, we have a normally open liquid level switch, right? So that'd be used in like a septic tank or a water tank or something, okay? Right, then we have, I'll let you guys read through the descriptions here. It's pretty common sense. We have a normally closed liquid level switch. So if the tank fills up, you want that motor to stop pumping water into a tank. It's going to push up and open a circuit here, cutting off the motor, cutting off the pump. All right. Unlike this guy here, if the water gets too low, it's going to open up a switch here, right, signaling for your motors to turn on and start pumping water, etc. Right? We have thermostats here. We're at a temperature switch. So it'll be a normally open temperature switch and a normally closed temperature switch. All right. Then we have limit switches, so pretty much how far something may travel on a conveyor belt, or your, say, your garage door, how far it's until when it's opened or fully closed, right? It's going to automatically stop opening or closing. So those are limit switches. So we have normally open and a normally closed. Again, based on gravity, whether it's pulling down or not on your pole. All right, there's a float switch here. The internal base based on, okay, these almost like an armature, and based on this ball where it's going to be located, it's going to push contacts open or closed. Again, another pressure switch or limit switch. There's a limit switch there. It's going to physically, mechanically, something's going to hit it and push it and say, okay, open contacts or closed contacts. Right. Okay, so de-energized means the self state. So switches in spring-held position. So you're going to have, say, an armature on a relay. Okay, it's being held by a spring, and that coil, when it's energized, is going to overcome that spring and pull down or push up or whatever an armature. Right. So the switch is in spring-held position. Right, so again, normal state when you're buying it off of the shelf at Home Depot. No pressure, okay, and pressure lines like vacuum or pressure lines, okay. No liquid in tanks, and room temperature, right? So not too hot, not too cold. So here we go. This is an example I was telling you about. It's asking which one is a normally open liquid level switch. So you got to ask yourself, in the normally open state, right, when you buy it off the shelf at Home Depot, what should it look like? This one here, right, it has the pole not in contact with your terminal here. Again, it's drawn with no liquid, no nothing, right? This one here, the pole is not in contact with this terminal, but what would gravity be doing in the normal state? It should be pulling this down, which means something is pushing this up right now, right? So this is not in the normal state. This is actually a normally closed float switch, and this would be a normally open float switch or liquid level switch. All right, here's a simple schematic diagram. They're asking what's going to occur if I push button 1 down. All right, so push button 1 here on the secondary side. My control circuit and my power circuit. Again, control circuits have the control device in it. Power circuit's going to be usually a higher voltage, but it's also going to have your contacts and your real load in it. Okay, so if I push button 1 down, I'm going to have current going to my control relay, the coil. My coil is going to energize, turn into a magnet. My armature is going to move. which is going to change the state of the contacts in the power circuit. So these are going to close. You got CR, CR, which means these are being controlled by each other. When that contact closes, I have current now going to my light. This one here says what occurs when a start is pressed down. Okay, so I got the secondary side, again, control circuit here. And I'm thinking that they're showing here a power circuit, but whatever. All right, so if I push the start button here, it's going to energize this coil, right, which is going to close these contacts here and here, which is turning on my light. But these contacts here are called holding contacts, right? When I push the start button down, it's going to energize this coil and change the state of these contacts, which is going to have now a path for my current to flow to this coil. So when I release my finger or the pressure off this start switch, again, it's a momentary, when it opens up again, I still have current traveling through these normally closed the normally open contacts, which are now closed, going to my coil, and it's going to maintain the circuit. So pretty much I don't have to stand at the start button and hold it down the whole time I want the light on, right? So it's called a holding contact. All right, here's another example of your control device or control circuit and your power circuit. They're asking what's going to happen if you press D down. So again, here we see that we have normally open push buttons, so our start buttons are always going to hook up in parallel. We can have 1 or we can have 50. Okay, regardless, we're going to all be hooking up in parallel with one set of holding contacts beneath them, right? And then our normally closed push buttons, our stop or our safety devices, are always going to be hooked up in series. So I can hit any of them, it's going to kill the power. Okay, so if I hit D, I'm going to have current going to my coil. It's going to energize, close these contacts, which is going to hold the circuit on. And these two contacts are going to change state. CR5 is going to close, CR6 is going to open. So turning on light 1 and turning off light 2. All right, so designing a schematic diagram. Okay, design a 120 volt schematic that is fed from a single phase 3-wire source. The following criteria must be met. A relay coil is energized when a single pole, single throw switch is closed. Okay, so that's going to be my control device. When the relay coil is energized, a red light will come on and it's going to stay on. When the relay coil is de-energized, so the switch is opened, a blue light will be on, but the blue light will turn off when the coil is energized. Right? So the materials you have for the circuit is a 120 volt AC relay. You have one red light and one blue light, and a single pole, single throw switch. Okay? So what I want you to do is I want you to draw out this schematic diagram. Okay? So it's going to be a 120 volt relay. All right? I want you to draw it out using your control circuit and power circuit, right? And try to figure out how to pretty much design a schematic diagram based on the sequence of operation that they're telling you right here, all right? So give yourself a few minutes, draw it out, and after this video, we'll go through it together. And yeah, good luck. Thanks for watching. If you have any questions, please feel free to always ask. You can email me, call me. We can do a Teams meeting, whatever you need to do. All right? Don't be shy. Thanks for watching. Take care.